Before we move on to charged black holes, let us review some of the essential mathematics. Suppose we have a point in 3D space at some coordinate. We can label its position with a vector. Let us call this vector x. The superscript I is not an exponent, but an index label. It can range from 1 to 3, with x1 being equal to the x-coordinate, x2 being equal to the y-coordinate, and x3 being equal to the z-coordinate. If we consider a point at some time t, then the index on x is mu, and it can range from 0 to 3. The 0 component is the time component, and it is multiplied by c, so that all components have the dimensions of length. X is then called the position 4 vector. Of course, the spatial components do not have to be in Cartesian coordinates. If we set c equal to 1, and everyone agrees that it is still multiplying the time component, then we can choose to ignore this factor. Let us now talk about Einstein notation. Suppose we have a regular vector v in Cartesian coordinates. Representing the components as v with a superscript and the basis vectors as e with a subscript lets us write the vector in terms of vi and ei. This is represented by a sum over I from 1 to 3. If we do not write the summation symbol, but everyone agrees that indices appearing twice in one term means it is summed over, then we can save some space and simply write the vector as viei. This is Einstein notation. Anytime you see indices appearing twice in a term, you must sum over all their values. Suppose we have a matrix eta with two lower indices mu and nu. Just as the index I labeled the vector elements, mu and nu can label elements within this matrix. Mu will label the rows, and nu will label the columns. As an example, eta 0, 0 will be the first row, first column. Eta 0, 1 will be the first row, second column, and so on. Putting this matrix aside, let us write the flat space Cartesian metric again. This is called the Minkowski metric. We can rewrite this, but explicitly showing our position 4-vector notation. Remember that x0 was t, so that dx0 just means dt. The same logic applies to the spatial components. This now just looks like our eta matrix summed with two copies of the differential. Remember that indices appearing twice in one term means we sum over all the possible values. Let's show that this really is our metric by writing out this summation. To do this, let's choose to start with mu equals 0, and then let nu range from 0 to 3 and sum all those terms. Once that is done, set mu equal to 1, and then let nu once again range from 0 to 3 and sum those terms. This will, of course, continue until the end when our mu and nu are 3. Now notice that our eta components are 0 for mu not equal to nu. That is, our non-zero components lie on the diagonal. This means that every term with mu and nu not equal will be 0, so we will only be left with 4 terms. Now, we can put the components from the matrix in and also put t, x, y, and z in for x0, x1, x2, and x3. We get back our metric. For a general metric, we use g mu nu instead. Of course, g will not necessarily be diagonal. You will often see the metric ds squared be written this way instead of writing out the entire thing every time. It seems like the true useful information about the line element is contained within g, and the differentials can just be added on by inspection very quickly if you know which coordinates you are using. G is then called the metric tensor, and it is arguably the most important object to know about in general relativity. Having a solid understanding of this will be crucial. Often people will use the name metric tensor and metric interchangeably. You may be wondering why sometimes indices are superscripts and why some are subscripts. This is to indicate components being contravariant or covariant. We will not go into too much detail about this because what is more important is how to lower or raise the indices. Let us return to our position 4 vector. The raising and lowering of indices is done with the metric tensor. The index nu appears twice in this term, so it is summed over. The index we sum over didn't have to be nu. We could have used any arbitrary variable. These summed-over variables are called dummy indices because their only job is to show that there is a sum. Going back to the eta matrix we had earlier, I will label this with G as we will define quantities for an arbitrary metric. The eta matrix was the Minkowski metric tensor, the flat space metric tensor in Cartesian coordinates. Again, we can write out the sum and get each component of the lowered x vector. The matrix is diagonal, so only one term is left over from each sum. We then see that the lowered x vector is the same as the original, but the time component has a flipped sign. Now, let's see what the following quantity is. Again, we have 2 repeated indices in a term, so this is a sum. This is relatively simple because this is just each component of the vectors multiplying together. The spatial part is one that you are all familiar with. The simple dot product of a vector with itself, or the squared norm of a vector. Remember that to get the lowered x vector, we used the metric tensor to lower an index. That quantity then was multiplied by the original raised x vector with a sum. This is then just a sum over 2 indices. Instead of the position 4 vector, let's generalize this to an arbitrary vector A. Because the metric tensor gave a negative on our time component, this quantity then can be negative, 0, or positive, corresponding to a time-like null or space-like vector. From previous videos, we should know a little about what these mean. Because of the negative component, you can see that taking the square root may give an imaginary result. So instead of calling it the squared norm, we just call it the norm. If we had 2 different vectors, then this is called the inner product. Let's continue exploring the properties of the metric tensor. The metric tensor will always be symmetric. That is g mu nu equals g nu mu. The transpose is equal to itself. The inverse metric tensor is defined such that it is g with raised indices, and the determinant of the metric tensor is commonly written as g without any indices. Now, let's look at something a bit more complicated. The christoffel symbols which appeared in the video of Newton's law in curved space. Here there is one upper index and 2 lower indices. The first thing we can do is distribute the inverse metric tensor term on the bracket. In each of these 3 terms, notice that the index row appears twice. We must sum over this index for all 3 of our terms. We also have a partial derivative term, which for the mu index is just the partial derivative with respect to x mu. If mu was 0, this would be a partial derivative with respect to t. Let's do an example. Suppose we want gamma 0 to 3. Then we set every lambda to 0, every mu to 2, and every nu to 3. Now, only the summation indices are left. We must sum from 0 to 3 for each of our 3 terms, so we should have 12 total terms. Remember that our metric tensor has 2 indices, and we represented it by a matrix where the first index was the row and the second index was the column. Now that we have 3 indices, we can represent it as a row where each component is itself a matrix. I also said in previous videos that non-zero christoffel symbols themselves do not necessarily mean that there is curvature present. That job is done by the Riemann tensor. This is typically the highest rank tensor that you will see in standard general relativity. The Riemann tensor is composed of the christoffel symbols. There is a sum over lambda in the last 2 terms. Just as with previous quantities, we can lower and raise indices with the metric tensor. If we sum the Riemann tensor with the first and third index, we get the Ricci tensor. This is what you will see in Einstein's field equations. Summing over every index, we get the Kretschmann scalar. This is what showed that we had a true curvature singularity at r equals 0 in the Schwarzschild metric. With 4 indices, we can represent the Riemann tensor as a matrix of matrices. While the 256 components seem like a lot, there is a lot of symmetry. There is only 20 independent components. But the point remains. If any component of the Riemann tensor is non-zero, you are dealing with a region with curvature.